In this video, we're going to be looking at the last section of the organic chemistry, which is topic 4H, synthetic polymers, and we'll be looking at the double content of the IGCSE chemistry course from Edexcel. So we're going to be looking at addition polymers and what that actually means and how they're formed. You should be able to draw the repeat unit of 4 polymers: polyethene, polypropene, polychloroethene, and polytetrafluoroethene. Be able to deduce the structure of a monomer from a repeat unit and vice versa, and then explain the problems with the disposal of addition polymers, so being able to go into some detail about their inability to biodegrade and what happens when we incinerate them. And as usual, we'll finish off with some past paper questions. So addition polymerisation is a reaction that you have actually met part of before. So back in topic 4D, when we were looking at the alkenes, you looked at addition of halogens onto alkene substances. Now what we want to do is, rather than adding in a halogen, we want to take those alkene molecules and we want to add them together. And this is known as polymerisation. And polymerisation, the definition, is the joining of many small molecules, and we call these monomers. Mono meaning one, and the mer meaning unit. So one individual unit joining together to make one large molecule known as a polymer, where poly means many, and again the mer means unit, so many units. So what happens this time is the alkene monomers are going to break their carbon-to-carbon double bonds, and instead of adding something on, they are going to add to each other, and they're going to form this long chain. So we don't form any other products, just this polymer. This reaction is going to happen at very high temperatures, and sometimes we need an initiator just to kickstart the reaction, but you're not going to be asked about the initiator in your exam. All you need to know is that it requires a high temperature. And we call this process addition polymerisation because it is the forming of a polymer, which is the polymerisation part, and it is an addition reaction, meaning it is alkenes reacting together. So what does this actually look like? Well, we have something like this. So we have lots and lots of ethene molecules. So remember, ethene is C2H4, and you can see this time, rather than writing out the actual atoms, we've just simply used circles. So the black circles are our carbons, and the white circles are our hydrogens. And we have got all of these different ethene monomers. So you can see in the centre that we have this double bond. Now, when we get this high heat, high temperature, high pressure and an initiator, we're going to break those double bonds. And when the double bond breaks, it only breaks one of them. So we keep one of the bonds as a single bond, and then we form bonds in between. And we get a substance that looks like this. And you can see now that we still have the carbons and the hydrogens connected in just the same way. The only difference is now, rather than double bonds, we have all single bonds. And at the end, we have bonds here, and these are known as extension bonds. And they're simply there to tell us that this is just one small part of the polymer, and the substance actually extends further and further beyond what we have on the screen here, because our polymer chain length could be up to 40,000 carbons, and of course we're not going to draw that in an exam, so we're only drawing a small part. So it's important that we include those extension bonds just to remind us that this is only a part of the molecule and it actually continues on and on with more chain. So what are you going to have to do in an exam? Well, there are 3 key structures that you're going to have to be able to draw relating to polymers. And you either may have to draw them or identify them. And we're going to stick with using ethene, which is C2H4. This is the easiest polymer that you will come across. There are some more challenging ones that we'll look at in just a few minutes, but this is the most simple one. So the first thing that you need to be able to draw is known as the monomer, and that is the alkene unit that is going to make up the polymer. And that is simply just the displayed formula. But we're going to draw it in a very specific way. You're going to have the carbon-to-carbon double bond like that, and then you have your bonds to the hydrogens above and your bonds to the hydrogens below. So make sure when you're drawing out the monomer that you do not have any bonds coming out to the left or to the right. You have the carbon-carbon double bond, and then you have above and below. You have nothing here or here, because it's just making that more difficult for you. So this is the monomer, which is simply just the alkene. Then we have to be able to draw out the polymer. And when we draw out the polymer, we're actually only drawing a very small section of it. So we're going to stick with this monomer, and what we're going to do is we're going to break the double bond down into a single bond. I still have my hydrogens, and now all I'm going to do is add in my extension bonds. So rather than having the double bond, so I'm going to just remove these arrows just so they don't confuse you. I'm going to remove the double bond, make it into a single, and then add my extension bonds. And to show that this is part of a polymer, I add square brackets on the outside, and I put the letter N outside it. And that simply means that my polymer is made up of this particular unit that repeats over and over N times. And N can be any number. We use N because not every polymer has the same number of units. So we just make that an arbitrary number. So that's the polymer. You then also have the repeat unit. And this is exactly what it sounds like. It is the unit that repeats over and over. So what we do is we take what we've drawn with our polymer, where we have our carbons connected to the hydrogens, with our extension bonds, and this time we just simply don't draw the square bracket and the N, and that is our repeat unit. So you can see that these are very similar. So the monomer will always have the double bond. The polymer will have a single bond plus the extension bonds. It will have the bracket, and it will have an N. And your repeat unit will simply have the single bonds and the extension bonds. But I haven't actually changed my carbons, and I haven't changed the hydrogens. So the good thing is, where the hydrogens are located, they could become any element or any group of atoms. It does not matter. I do the same thing over and over to get my monomer, polymer, and repeat unit. I don't make any changes to the elements that are involved. I'm only making changes to the bonds. And that helps us when we start to look at different substances. So just to go into a little bit more detail about polyethene. So polyethene is formed from the monomer ethene. Now you can see that in order to name it, I simply write the monomer's name, I put that in brackets, and I write the word poly in front of it. And that goes, again, same thing, regardless of what the monomer is. So in this case, it's polyethene, and there are actually two different types. There's low density polyethene, or LDPE, and this is very flexible, but it's not particularly strong. And you will have come across this probably almost every day of your life, if not at least every week, because these are polythene bags, or what you might find in a supermarket. So those plastic bags that you use when you go shopping, they are low density polyethene. Now we also have high density polyethene, or HDPE, and again, you'll come across this probably every day of your life. It's very rigid and strong, and it's used for things like plastic bottles. So any milk cartons or juice bottles like Coca-Cola or Mountain Dew bottles, they are made of high density polyethene. And you can sometimes see that written on the bottle itself. You can see PE engraved into the bottle just to tell you what it's formed from. Now, another polymer that we need to know is polypropene. So this time made from the monomer propene, but notice we've kept that same structure. So we have our two carbons joined together with our double bond and our two groups on top, two groups on the bottom. All I've done this time is swapped out a hydrogen for a CH3. But the way I would draw out my polymer is exactly the same. I remove my double bond, I add in my extension bonds, my square bracket, and my N. So keeping it all very simple. Now, polypropene is slightly stronger than polyethylene, and it is used to make things like ropes, crates, or fibres for carpets, or even for clothing. So you may see polypropene in fibres when you're looking at a label to show what's in your clothing. We can also have polychloroethene, and it's formed from the monomer chloroethene. So this time I've swapped out a hydrogen for a chlorine. Again, notice the way I draw out my polymer is exactly the same. Sometimes this is known as polyvinyl chloride, or as you probably would know it, PVC. Again, you've seen PVC, you've probably seen it in the classrooms of school. Any sort of plastic covering tends to be made as PVC because it's very strong, it's rigid, and it is an insulator. So what you'll sometimes find is a plug will be coated in a PVC polymer so that you're not touching any of the wires. So it tends to be used for things like water pipes, replacement windows, sheet floor coverings, or any sort of electrical insulation. And the last polymer that you need to know is called polytetrafluoroethene, or PTFE, and it is formed from the monomer tetrafluoroethene. And all that means is I've taken the ethene and I've replaced the hydrogens with 4 fluorines. So tetra means 4. So I have 4 fluorines attached to an ethene, and then I can draw out my polymer. And PTFE tends to be used as a coating in non-stick cooking pans, and it is very, very unreactive. And this is because it has very strong bonds between the carbon and the fluorine, so they're not broken very easily. So because it's very unreactive, we can actually use it to line containers of very corrosive chemicals because it's not going to react with them. Now, one thing that you have to be able to do is you have to be able to deduce a monomer from a polymer. So we've looked at going from the monomer to the polymer, where we take out the double bond, add the extension bonds, add the square brackets and the N. In an exam, you have to be able to go the other way. So they could give you a polymer structure like we have here. So this is polystyrene. Now, you've never seen polystyrene before, you've probably heard of it, but you've never seen this structure. But that does not matter. You can still work out the monomer from this. All you have to do is just take any 2 carbon atoms that are next to each other. So you can see that we have these 2 here, and we're going to remove them from the structure. So when we remove them from the structure, we get this, which is our repeat unit. So we've got our extension bonds, our carbons, and then this C6H5. Now all we're going to do is get rid of these extension bonds, or sometimes called continuation bonds, and then we're going to replace the single bond with a double bond. And this is then the monomer. And this monomer is known as styrene, because remember, we name the substance as poly, and then in brackets the name of the monomer. So we just remove that. So this is styrene, which has got our carbon-carbon double bond with 3 hydrogens and C6H5. So we're just taking that from the structure. So if we look at an example here, we can see that we have this polymer. We're going to take any 2 carbons together. So let's take these 2 from the center here. I'm going to redraw what this looks like with my extension bonds, and this is my repeat unit. So to go to my monomer, I remove those extension bonds and make that single bond into a double bond. and that we get a substance that looks like that, and this is actually chloroethene. So that's being able to deduce the monomer from the polymer. Now moving on to the disposal of polymers. So the majority of addition polymers are actually recycled. So you'll have heard about recycling plastic bottles, recycling polythene bags. This is a huge drive that the majority of the world are pushing forward so that we're not wasting these very useful substances. And it also saves on the raw materials. All of these addition polymers come from crude oil. So from the crude oil, we get the alkenes that we need in order to make these plastics. So if we do not have crude oil, or we start to run out of crude oil, which we know is the case because remember it is a fossil fuel, which are finite resources, we eventually will run out of these plastics. So if we can save on the raw materials and start actually recycling more, then we're saving us using up that crude oil quite as fast. Now, the biggest problem with plastics is that they are non-biodegradable. So when we're saying plastics, we are referring to these polymers that we've been looking at. So when they are non-biodegradable, it means they're not going to be broken down by the bacteria in the environment, and it's because they have very strong covalent bonds. So at normal temperatures, they are very inert or unreactive. So that means that they're just going to remain in nature, not breaking down for thousands of years, which is why you should not just throw them away. So if we don't recycle plastics, which is a small proportion of the plastics that we use, there are two main ways that we dispose of them. The first one is using a landfill, and the landfill is basically a huge pile of plastics and waste that are then buried in large holes in the ground. However, they remain there for thousands of years, and landfills are quite unsightly and we don't really like to use them, but it is one possibility. The other possibility is incineration, which is just another way for saying that we burn the plastics in order to break them down. Once we get to high temperatures, the bonds are able to break and they are able to undergo reactions to break down, which we don't get at normal temperatures. Now, the benefit of this is it can be used to generate electricity. However, the incineration of plastics releases carbon dioxide, which we discussed in topic 2D, leads to global warming, and it can also release toxic gases such as hydrogen chloride, and that's not really something that we want to be breathing in. So what you need to be able to do is you need to be able to identify the advantages and disadvantages of each method. So landfills, the good thing is there are no greenhouse gases or toxic gases released, and it's very cheap. Biggest disadvantages though for landfills is they're ugly, they're smelly, they're noisy, nobody wants to live near essentially a giant rubbish site. They use up large areas of land that could be used for more useful things like housing or food sources, and the waste is going to be there for thousands of years because they are non-biodegradable. Now, incineration, the advantages are it doesn't require a lot of space, it literally just requires the oven that we need, and it can produce heat, which can be used for local homes or offices, or we can use the incineration to produce electricity. And the biggest problems with incineration is it's expensive to build and maintain a plant. So if you have an incineration plant, you have to build these ovens capable of these high temperatures, but you also have to employ workers. Those workers then need a salary, they need their benefits, they need to have all the overheads at the factory, all of that stuff, it adds up and it can be quite expensive. They also release toxic gases and greenhouse gases, which is not good for the environment. And when we get the ash that is produced, so what's left over after incineration, we then have to put that in a landfill site. So again, not only are we getting the disadvantages of incineration, we then get the disadvantages of landfills. So in reality, the best way to get rid of any plastics is to recycle them. So if you do use any plastics, we do strongly encourage that you recycle them, not just for the sake of the environment, but also to help save on these raw materials. Now let's finish off by looking at some past paper questions on polymers. So ethene is used to make polyethene, and it shows you the example here. So we have our monomer and we have our polymer. Now they've drawn out the polymer slightly different here, where they've just shown the 3 units all joined together and they have the brackets, and we could have an N outside of this, but it doesn't matter. And we want to know, first of all, what's the name given to this type of polymerisation? Well, we've only learned one, and it is called addition polymerisation. And we know that because we have this addition reaction between the double bonds. And then using the diagram, we want to state 2 changes that occur during the formation of this polyethene. So the first thing is that one of the bonds between the carbons breaks. So we go from a double bond to a single bond. So you can say that it changes from a double bond to a single bond. That would also be accepted. And then what happens? Well, we have the ethene monomers joined together in a long chain. So we can see that's the main thing that happens. So we break this double bond and then they all join together. That's our second mark. Then we want to show the structure to show the part of the polymer formed when 2 molecules of C3H6 are formed. So C3H6 is propene. Now with a question like this, they don't give you the monomer, so you might want to draw that out. So remember, we're going to have our 2 carbons with our double bonds. We're going to have our hydrogens, and then one of these carbons is then going to contain a CH3. That is our propene. Okay, so remember, we always want to have it as the 2 carbons with the double bond and our 4 things attached. So now all we do is we just break that double bond and then we can add it in here. So we have a CH3 and a hydrogen and then 2 hydrogens. And we repeat that over, a CH3, a hydrogen, and 2 hydrogens. So we went from this monomer to this polymer. 2 marks. So you get 1 mark for making sure that you have your CH3s and then all the rest for your hydrogens. Now we want to look at what is meant by the disposal. So the disposal of most addition polymers is a problem because they do not biodegrade. We want to be able to state, what does that mean? Well, biodegrading means that the polymer breaks down, and that's the first part, and then we have to say how it breaks down, and it is by bacteria, or you could even say microorganisms. Okay, so it's a natural breakdown, but you can't simply just say natural, you have to say what causes that natural breakdown. So it's bacteria or microorganisms. And the property that prevents the addition polymers from easily biodegrading is the fact that they are unreactive. Or you could even say inert. Either one of those would be accepted as an answer. So there's the answers to the first part of the past paper questions, if you've been trying these at home, and then the second part. Now that's everything for topic 4H, synthetic polymers, and that is the end of the organic chemistry section. I would recommend that you do practice drawing out the monomers and polymers of each of these polymers that we've looked at in this presentation. I would also recommend that you try some of the textbook questions because it will give you some more unfamiliar polymers to try. If you do have any questions, feel free to leave a comment below, and we hope to see you back on the channel soon.